Hello, this is Doug Schmidt. We'll be starting the webinar here shortly for the POSA MOOC on concurrency. Just waiting to see for people to join. All right, it looks like the picture is working, which is good. So hopefully people will join momentarily. If you join and can hear me, please let me know so that I will be certain that the sound is working properly. I see a couple of viewers have joined. We'll be starting shortly. Okay, let's go ahead and get started. Welcome to the next live lecture and virtual office hour for the POSA MOOC. What we'll be covering today will be the Async Task framework, and I will also go over the skeletons for the next programming assignment. If you have any questions about the current programming assignment, or if you've had a chance to take a look at the skeletons for the next programming assignment, please don't hesitate to ask, and I'll be happy to answer them. So why don't we go ahead and start, and we will start off with the Async Task material. Let me get that all set and ready to go. Share my screen here. So today we're going to talk about the Async Task framework. And as you'll discover in our coverage today, we'll be talking about some of the concurrency idioms and mechanisms that are associated with programming the Async Task framework in Android. As you'll see, the intent of this framework is to allow applications to perform background operations and publish results on the UI thread without having to explicitly manipulate threads, handlers, messages, or runnables. And that, of course, is in contrast to the Hammer framework that we talked about last time. So let's first start by talking about what the Async Task framework is. And we'll start also by motivating how it compares and contrasts with the Hammer framework. So classes in the Hammer framework, as you might have noticed in our discussion last time, are rather loosely connected. So this flexibility works pretty well for simple use cases where you've got a background thread that wants to pass a runnable to the UI thread, either by posting it to a handler or by calling run on UI thread. And then the main thread will turn around and pick up that call via a run method callback in the main thread and do its thing. However, there are some drawbacks to this approach. One thing that you have to do in order to use the Hammer framework properly, you really have to understand the various pieces involved. You have to understand messages and runnables and threads and handlers, and you don't really have to understand some of the internal details like looper and message queue per se, but you have to kind of know what these pieces are. You have to be aware of them. And really what this is under the hood is the command processor pattern. So you have to kind of understand how that pattern works. The solution is also somewhat tedious and error prone. Some of the reasons why it's tedious and error prone is that you have to be very careful about the life cycle of the activity that you're talking to. If the activity goes away while you're trying to do a run on UI thread or post to it, you may have some problems, and it's very hard to figure out workarounds for those problems. Moreover, there's just a lot of pieces involved, and you have to make sure all the pieces work, and you've got to get the variables scoped properly, and so on and so forth. In contrast, the classes in the async task framework are strongly connected. And what that means is that they have more pieces that are cohesive. So we've got basically the async task, which internally has an executor that's running, and it hides the future task and handler from the application developer. And so as a result, you as an application programmer don't have to know anything about threads. You don't have to know anything about handlers or runnables or messages. You just have to know how to make method calls on an async task object, which is a pretty straightforward thing to do. And then magically, things show up in the UI thread via callbacks using something called the template method pattern. So this gives you all these nice features of concurrency without exposing all the other low-level mechanisms to you directly. In some sense, this leads to a smaller surface area. In other words, the number of things you have to know to use the async task framework is more cohesive, and it's all localized in one place. You just go read the async task class description and you know how to use it. Whereas with the Hammer framework, you have to go read about handlers and activities and threads and messages and runnables and so on. And so it's more dispersed. The surface area to understand the elements is more dispersed. The async task basically hides all these details via something called the facade pattern. You can read more about the facade pattern here. It's just a pattern that pushes the details behind nice, clean, abstract interfaces. There's some other patterns that the async task implements as well, and we'll talk more about them later. So basically, we use facade to wrap the complicated internal framework that async task provides with a simpler interface. And later on in the course, we will actually go into some detail about what the internals of async task looks like. We'll cover that next week when we talk about the internals of all this stuff. So let's talk about some of the methods that are provided with async task. There are two basic types of methods or classes of methods in the class. One of the methods are public methods, and these are the methods that are actually invoked by the applications. And so, for example, we have async task, which is the class that's created, and it has a method called execute. And execute takes one or more parameters of a particular type, and it has those parameters executed in the background. What happens by default in later versions of Android, the recent versions of Android after Honeycomb, is that each call to execute on an async task runs one at a time serially in a background thread within a single process. So if you have, what I should say more specifically is if you have a bunch of async tasks in an application or in a process, then by default, they will run one at a time, one after another, using something called the serial executor. Obviously, if you have different async tasks running in different processes, then they will run concurrently potentially. But if they're in the same process, the same application, then they run one at a time by default. There's also another method called execute on executor, which can actually be used to run the task in the background via an executor. And an executor, as we'll see later, is basically a mechanism for being able to run a task which may in fact be mapped to a pool of threads. So there's actually something called the thread pool executor, and if you use that, then your execute on executor calls actually run concurrently. And that's a win. You can actually get a speed up depending on how you configure your executor to run things much more concurrently and simultaneously. There's also a simplified version of execute that just runs a runnable. That really is just a front end, very, very thin front end to the underlying executor that's going on there. You could just use a Java executor if this is all you're going to do. And then finally, there's another method called cancel, and this is used to attempt to cancel the concurrent execution of a task, if possible. And you can see here that you can give different flags to indicate whether or not you want to interrupt it if it's running or not. And we'll talk more about that later. That's quite a bit like thread interrupt in Java threads. In particular, cancel requires cooperation by the async task implementation. It's voluntary. You have to program your app to check to see whether it's been canceled or not. And we'll take a look at that when we talk about other parts of the solutions. There's also a number of protected hook methods. These are the ones that you have to subclass and override. So an app will come along and override one or more of these methods. There's one that you always have to override. The other ones can be overridden optionally. And these are invoked by the async task framework at different points of time and in different threading contexts. So let's take a look and see how these things get called and how they work. So as we'll see, async task has to be extended, and one or more of its hook methods have to be overridden. And this turns out, by the way, to be the template method pattern, and we'll talk more about that shortly. So the execute method or the execute on executor method, they're both the same from the point of view of what we're talking about here. They can only be called once per instance of an async task, and they have to be called by code in the user interface thread. And this is implemented internally as a template method, which you can read more about here. The template method pattern is a gang of 4 pattern from the Design Patterns catalog book, and it basically says implement your logic in a base class method or a superclass method, and then have that method have callouts to hook methods or so-called primitive operations that can be overridden by subclasses. So yeah, that's what we would do. We would inherit from async task, and we would go ahead and implement various methods. I'm just assuming we have some fictitious image download task here that's going to do a bunch of things. We'll look at some examples later. So the on pre-execute method is invoked by the async task framework in the context of the user interface thread, and it's intended to perform any initialization actions that you might have. These are optional. You don't have to have them. In other words, you can omit overriding on pre-execute, and it does nothing by default. It's just a no-op. The do in background method, on the other hand, is invoked by the async task framework in the context of a background thread to perform long duration operations. So you can use this to run things that'll take longer to run, and that's a good way of being able to offload work from the main thread. There's also a method called on progress update, and on progress update is invoked by the framework in the context of the UI thread when the background thread calls publish progress. And that's a way for the background thread to periodically or occasionally notify the UI thread of something, like you might update a status bar or a progress bar to indicate how much work you've done relative to how much you have left to do. There's also a method called on post execute, and this is invoked by the framework in the context of the user interface thread when the do in background thread returns its result. So when do in background is done, then on post execute is what gets called in order to be able to handle the results. And there's also another method called on canceled that we'll talk about in a second. So it's also possible to cancel operations. And so if somebody cancels an operation, which is called by invoking the cancel method on an async task, that gives the application the opportunity to try to stop the execution of the task. Now, this is sometimes easier said than done. Obviously, if the async task is already finished by the time cancel is called, in that case, it's going to not do anything. Likewise, if you don't properly implement voluntary cancellation, then it also won't do anything. It's worth noting, by the way, that you can only call execute once per async task. If you try to call execute more than once, it will throw an exception and won't let you do it more than once. So don't try that. When the cancel method is called, it's invoked after cancel is called and do in background finishes, the on canceled method is called. So on canceled is a way of handling cancellation results or cancellation behavior whereas on post execute is used for the normal behavior. So if things finish normally, then on post execute is called. If things finish abnormally by being canceled, then on canceled is called. So these are mutually exclusive. If on canceled is called, on post execute is not called, and vice versa. You can also periodically make a method call to the isCanceled method inside doInBackground to check to see if the task has been canceled or not. And if it has been canceled, then that method will return true. And this is obviously very similar to Java threads and how they can check to see if they've been interrupted as a way to know whether they've been informed to shut down. So these are good examples of voluntary shutdown mechanisms. In fact, when we look at the code for async tasks much later, we'll find out that under the hood, it actually uses interrupted and is interrupted to do its work. Just to reiterate the point I made before, you cannot execute the same async task multiple times. You can only execute an async task a single time. Obviously, if you want to execute multiple async tasks, you can simply create multiple async task objects. Now, an async task is actually parameterized by 3 types, and these types are used by its various hook methods. And here are the 3 types. One is called params, and these are the types that are passed when you invoke execute, and it's actually used to pass to the to the doInBackground method. So that's what's used to pass the data. Progress is the type that's used to indicate what's passed from the publish progress method to the onProgressUpdate. That's where you can incrementally or periodically inform the UI thread that you're still making progress. And then the final method is result, and this is what's returned by doInBackground and what's passed as a parameter to onPostExecute. So what's returned by doInBackground is passed as the parameter to onPostExecute, and that's the result of the operation. Applications can customize async tasks to meet their concurrency needs. And here's just a very, very simple example. In this particular example, download task extends async task, and it provides URI as the params. It provides integer as the progress information, and it provides a long as the result. And so what it's going to do is when it's executed, when we execute this thing down here, we'll pass it in the URL, and that will then be taken here. It'll be passed in as a URI. That will then go ahead and run in the background, download the file or files, because you can actually pass more than one URL, but let's assume we just passed one. And after that's downloaded, or during the download, we can periodically call publish progress, and that will call onProgressUpdate, and that would then show to the user how much we've downloaded thus far. You could have a little progress bar or a spinner or whatever you want to do to indicate how far you've gone. A progress bar would make the most sense in this context. And then after this guy returns, he's going to return the number of bytes downloaded. So that's going to be a long, and that's going to come over here as the parameter to onPostExecute, and then we're going to print out the number of bytes downloaded in a dialog. And again, there's obviously lots of other things you could do for this application. This is not the only way to use it, and we'll see other examples shortly that are more interesting. Okay, and that's when you go ahead and execute the async task. Notice in this case, because there's really no need in this example to make an instance and store the instance, we make an anonymous instance and simply execute it. The only real normal reason that you actually store an instance of an async task is if you want to be able to cancel it later. So that's really the only reason that you would want to store it, because you're not going to be able to call execute on an async task more than once. If you call execute on an async task more than once, it will throw an exception. So let's take a look now at how we might program with an async task. And what we're going to do here is look at the example we started last time. First, I'll refresh your memory about what the example is, and then we'll go into more detail about how it works. And you can download this example here. So if you recall, we have a user interface. You can click different buttons to download things different ways. Those things get handled in various ways. So let's say, for sake of argument, we're going to run this as an async operation. And so then the run async method is going to get called. That's what's connected to the button. And then what will happen is the UI thread will go ahead and execute the request. that will then download the file in the background, the image in the background, and after it's finished downloading the image, it'll go ahead and display it in the onPostExecute hook method. And this is a very, very easy thing to do. And notice that you don't have to know anything about handlers or runnables or threads or messages or any of that kind of stuff. And that's also obviously an example of the template method pattern, where execute is the template method and onPostExecute and do in background are hook methods or primitive operations that are called when things get to a certain point. Okay, let's go now and take a quick look at the code that goes along with this. And I will stop sharing one thing and start sharing the other. Let's go share that code. Okay, so hopefully you can see that. Here is the code, and I'm just going to dive down here, go look into the view part, and I'll just quickly reiterate what we just showed you before, just so you got the context. Here is the run async task method. This goes ahead and gets the URL string that was passed in by the user, hides the keyboard, and then it creates a new async task, and it executes the async task, passing in the URL that was passed by the user, provided by the user. And notice it's an anonymous object, so it just gets run one time. Here is download with async task. As you can see here, this goes ahead and stores a weak reference to the activity. Now, there's a bunch of different ways of handling these kinds of things. As we'll talk about this a little bit later when we talk about usage considerations. But in a nutshell, you have to be very careful if you have dependencies between the async task methods and the ones that are being used in the activity. And we do have those dependencies here just to illustrate the point. You especially have to be careful with dependencies that happen in the do in background method. And I'll talk about that as we go through here. So here's the on pre-execute method. Notice that this uses the weak reference to call up to a show dialog method in the activity saying we're downloading with async task. This gets called in the UI thread after execute, but before the do in background method runs. Here's the do in background method. This runs in the background. As you can see, it goes ahead and it downloads the bitmap and returns it as the return value of the method. And then that bitmap that's returned is then passed back to the UI thread, and we go and dismiss the dialog and display the bitmap. Now, the thing you have to be careful about here is what happens if the activity were to disappear while you're in the midst of the download. And you have to be very, very careful with this. This particular approach is not going to heroic lengths to solve this problem. I will show you examples later with the model view presenter pattern that are going to go to heroic lengths to make sure that you don't have problems if the activity has disappeared. Now, it turns out that the way things work in Android, by the time that the onPostExecute method is called back, under most circumstances, the activity will be up and ready to go, even if you've had a reconfiguration change take place. And that happens, that occurs because of the way that the semantics of runtime reconfiguration changes occur in Android. But you still have to be very careful. And so if you're really, really paranoid, there are techniques you can use to store the results if you're not able to get access to the activity. And you can store them in something called a retained fragment. And then you can fish them out later once you've gotten reconnected, and then print them as the opportunity avails itself. And we'll talk a little bit more about that later. It's a more sophisticated use case, and it's not widely done in practice. But if you really are paranoid about not having problems with runtime reconfiguration, and you're not using the if you're not using the model view presenter pattern stuff that we're going to talk about more, then there's some other things you have to do, and I'll talk about that in a second. Okay, so that's an example of how do in background runs in the background, produces a result concurrently, returns it back as a bitmap, that gets passed on post-execute, and then we call back to the activity in order to display it or dismiss it and so on. Okay, so that was the example. Let's now bounce back over here, and we will talk about usage considerations, which is the last piece of the puzzle. So there's a number of usage considerations to think about when you use Async Task. Obviously, the purpose of Async Task is to allow the user interface thread and background threads to communicate. And the main thing to remember is that the async task is really intended to be used with the user interface thread and background threads. There are some circumstances where you can kind of pervert this a little bit, which we'll talk about in the next MOOC, the Post-it Communication MOOC, having to do with using async tasks in services that are running in other processes. Got to be very careful. That is not really a use case that's explicitly documented, although in my experience it typically works. But you're better just thinking about using async task to allow the UI thread and background threads to communicate. It's more strongly connected than the Hammer framework, which is nice, so that you only have to know about calling execute, and it handles all the internal details, and you just have to know about certain hook methods that get called back. So that makes it cleaner. So you don't have to directly manipulate handlers, messages, runnables, or threads. An async task obviously embodies a bunch of key framework characteristics. It has inversion of control. So you give the control to the async task framework, and then it'll call you back when something interesting happens. It obviously has domain-specific structure and functionality. This is oriented to the domain of concurrent object-oriented programming in Android. And you end up with semi-complete portions of applications where an awful lot of the work is done for you by the async task framework itself, and you just have to come along and implement subclasses that override pieces of the framework. So you have to override do and background. That's really all you have to do. Everything else is optional and provided for you. There are some traps and pitfalls with async task, and if you take a look at this link down here, you'll read about them, and I'm going to summarize them briefly. So one issue, which is, by the way, the same issue as with threads, so there's nothing new here. Cancellation is voluntary. So if you cancel an async task, then that may or may not actually cause the async task do and background method to shut down immediately if you don't take steps to ensure that. So, but that's nothing new. That's a problem that you have with Java threads in general. There's also almost always a dependency on an activity, because you're typically creating an async task in the context of an activity, and it's going to want to have the async task run in the context of the UI thread. And if the activity has disappeared, you may have some problems, and you can have issues with memory leaks if you're not careful. There's also issues, and these are not unrelated issues, when the configuration changes. So if the phone is rotated, you rotate the orientation from landscape to portrait or vice versa, then during that time when you rotate, the activity that is associated with the async task may be destroyed and recreated. And so you have to implement a very careful protocol to make sure that you've always got the right activity reference, the right weak reference to an activity. And you've always got to use a weak reference, because otherwise you'll end up with memory leaks that'll occur, and you'll end up having your async task running in the background connected to a dead activity that is sort of a zombie that doesn't really exist anymore. Did I not share my screen? Darn it. Sorry about that. That was annoying. If I don't share my screen, please holler at me so I will share my screen. Tell you what, I'll start over again with that section, and I'll just fix it in the mix later. So there's a number of considerations to think about when you use an async task. So you want to be able to allow a user interface thread to interact with a background thread. That's the primary use case. In contrast, the Hammer framework can be used to allow threads that are background threads to talk to each other, but the async task doesn't support that. It's more strongly connected than the Hammer framework is. So you just have to know about a few methods, and it hides all the details from you. You have to know about how to do execute. You have to know how to do in background and various hook methods and so on. But you don't have to know about handlers, messages, runnables, or threads specifically, which is good. It embodies various characteristics of frameworks. It has inversion of control. It owns the event loop once you call execute, and it calls back your hook methods as they are needed to be called. It obviously has domain-specific structure and functionality because it knows how to handle concurrency in Android. there's a semi-complete application where portions of the application are handled by the framework, and you just have to override certain methods like do in background or on post execute. But the async task framework handles everything else, so it is providing you a large amount of functionality that comes out of the box. We'll look at that functionality later. There are some downsides with async task, however. You can read about them at this link down here. One problem is that when you try to cancel a task, it's just the same issue as canceling a thread. You can't cancel a thread non-voluntarily, just like you can't cancel a task non-voluntarily. So you have to be prepared to cancel, and so that requires some collaboration between the different parts of the program, but that's nothing new. That's the same thing as with any thread. There's dependencies on activities where memory leaks can occur if you have strong references to the enclosing activity, which means that if the phone is rotated or the activity goes away for some other reason, you'll end up with the activity not being able to be garbage collected if there's a strong reference from the async task to the activity. There's similar problems related to what happens when you rotate the phone in general, which causes the current activity to be destroyed and a new activity to be created. If you have code running in the background thread, and it's trying to access the activity while the activity is being destroyed, you obviously have a problem on your hands. And there are ways of dealing with this, and we'll talk about them, but you have to be very careful. And a good rule of thumb is to use the model view presenter pattern, which alleviates a lot of these problems because you don't have any attempt at trying to access view code directly from the background thread. And then there's also some subtle portability problems. The semantics of async task execute have changed over time. So initially they executed things serially, then for a period of time they ran them concurrently in an async task, and then finally they decided that was breaking too much code, so they switched back to the default behavior being serially. The way around this, of course, is simply to call execute on executor if you want concurrent behavior, or call execute on executor if you want serial behavior, and pass in the serial executor. The model view presenter pattern that we'll talk about more, and you've seen a little bit of, that addresses a lot of these problems. It alleviates the issues with dependencies on activities and losing results if and when configuration changes take place. So those problems can be solved by using the MVP pattern. And cancellation and portability can be addressed by simply knowing how to use the Java and Android programming patterns, things like interrupts and cancellation semantics being voluntary, and also knowing what API calls to make if you want to have portable code. Async task is used all over the place in Android. So it's very heavily used. It's used in the frameworks. It's used in the packaged applications. So if you want to see other examples, there's lots and lots of examples in Android code about how to use it. The on-progress update method is not all that widely used. There are a few places where it's used, and you can take a look and see, but it's not as widely used as the async task is itself. Okay, so that was basically the discussion of the async task framework. I will go back and do a post-production editing job on the slides to get rid of the gap where the screen isn't showing up. So anybody who wants to watch this later will see the complete or not quite nicely visualized solution. I'm happy to take any questions if you have them at this point. If you don't have any questions, what I'm going to do is switch over and start talking about the next programming assignment. So let's go ahead and bring up a browser here. All right, let me share my screen. So here is a screen. Let's bring this screen to show the class for a second. Got class, post of concurrency 3. So if you come here and you go to the programming assignments and assessments, then hopefully assignment 2 will be up, which it is. So you can go here. This explains what to do for programming assignment number 2. And obviously you can click on this link. It'll take you to the place where the code is. You can find the description of the assignment here, and you can find the skeletons of the source code here, and we'll go through them in a second. And we've also got some unit tests and Robotium test. So let's go now, and I will walk you through some of the code that that we have as part of the skeleton. So let's go over here. Okay, so we look in assignment 2, look down here. The Android manifest file is essentially the same as before, no real changes. In fact, most of the look and feel of the application is almost identical. There's an MVP file which we use to define the interfaces that the different layers in the model, view, and presenter are going to use. And we'll look at the methods that we need to in a minute. Here's the one for the model. This is the one that makes a Palantir manager and acquires a Palantir and releases the Palantir and so on. Let's go take a quick look at view. View is very similar to assignment 1. I'm not going to go through the Palantir application activity. This is pretty much identical to what was there before. Gazing simulation is very similar, but there's a couple of important differences. And let me show you what those are. The most important differences for the gazing simulation activity is that the various methods that are used to do things that change the way the screen looks. In other words, change the colors of the beings or change the colors of the Palantir. In the past, those things actually did the work directly to do the update the display. And for fun here, just to give you some experience with some async task features, I've changed these methods to return runnables. So mark being just returns a runnable that's going to do the work to mark the being. Mark free returns a runnable that marks the Palantir as being free. Mark used will return a runnable that marks the Palantir as being used. Mark idle returns a runnable that marks a being as being idle, and so on and so forth. So these are the various things. And let's see, I guess I could actually get rid of mark interrupted because we're not using that in this particular program, but I'll go back and zap that later. So anyway, everything here just returns runnables. I think what else is interesting here. So that's pretty much the main difference between what was in gazing simulation here and what was in gazing simulation before. Let's go take a look at the Palantir, or rather, I'm sorry, the presenter layer. As before, there are 3 files. There's being thread, which is identical to what was there before. This just creates a thread that will run a being. We have something called being async task, and this is the async task, and you'll have to fill in some of the methods here. And then we have the Palantir presenter, and the Palantir presenter, of course, is the part of the code that's going to actually kind of orchestrate everything. It's the interface into the presenter layer. This looks a little bit similar to before. I made a couple of changes to the last version. I got some good feedback that recommended that we change the name of generic model to generic presenter, which made a lot of sense. So generic presenter is now used as opposed to generic model. That's a little cleaner to understand. Most of the rest of this stuff is very similar. One difference is rather than having a list of being threads, we have a list of being async tasks, and we'll look at what those are in a minute. But other than that, a lot of the other stuff is the same. We also have a few new things that we need for the async task version. One is the use of a countdown latch. A countdown latch is an example of barrier synchronization. And this is what's going to be used in this solution to have the join thread wait for all the async tasks to shut down. I provide you with the bulk of the code for doing this, so I'm not going to go into a lot of detail about how it works, but if you're interested, there are some videos you can watch that tell you more about what a countdown latch is and barrier synchronizers. Here is the thread factory. Thread factory is used by the thread pool executor to make the appropriate kind of thread in a thread pool. And so here is what you're going to have to do. You're going to have to implement this method called new thread that will make a new thread. And then you'll also have to pass the m thread factory to the thread pool executor constructor later. We'll talk about that in a second. This is just giving you a little practice with factories. This is a good example of a factory method in the factory method pattern. The onCreate method initializes the superclass. well, I'm sorry, it goes ahead and weak reference to the view layer. It goes ahead and initializes the generic presenter and passes in the Voluntary model class. That'll be what's used to have a model layer. We get the intent that was used to start the activity. We figure out what its arguments were, and then at some point later, this code will get started and it'll start to run. This is what gets called the first time the presenter layer is created. The onConfiguration_change method is called back every time the activity is destroyed as a result of an orientation change. And as you can see, the main thing it does here is it goes ahead and sets a new view to point to the new view object that's passed in here, and it makes a weak reference to this to make garbage collection work properly. And then it indicates a runtime configuration change occurred, which will change the semantics of some other parts of the code when you push the start simulation and stop simulation button. So this is basically just resetting the view so that things are properly updated if the activity is destroyed. OnDestroy gets called when things shut down. It's a no-op in this case. Configuration change occurred returns whether a configuration change occurred. Make argv just takes the parameters that were passed into the intent and makes an argv argument that's used to initialize things, to include things like the number of beings, the number of palantiri, the number of iterations to run the program. Is running and set running are used to indicate whether the presenter layer should run. These are accessor methods to return the different colors that are used to color the different beings and palantiri. Here's the shutdown method. The shutdown method is going to iterate through all the tasks and cancel them. So this will call the cancel method, and you'll have to take that into account in the code that we'll talk about shortly. Here's the start method. The start method goes ahead and makes the palantiri manager in the model layer. It's the initial count of gazing task, which starts at 0, shows the being, shows the palantiri. Create the thread that'll wait for all the being threads to finish using the countdown latch. And then it creates and executes being tasks, as many of them as there are beings. And that's the method you have to implement. Here's join being tasks. This creates a countdown latch with the number of beings that can be running concurrently. And that latch is then going to be, the exit barrier is going to be used between different parts of the program here in order to coordinate shutdown cleanly. We create a thread that runs, it's runnable. The run hook method simply waits for all the being tasks to stop gazing. So it's just going to sit there and wait. After this thread is created, it'll wait for all the being tasks to stop gazing, and then it'll tell the UI thread that the simulation is done. So this is a little different from the previous assignment where you had to use thread join instead of a barrier wait. Here's the main method you have to implement. This is called create and execute being tasks. And I kind of outlined what you have to do. You'll have to create an array list of being tasks, and then you're going to have, that's the size of the being count. You'll then iterate through all these things. You'll create a new being async task that'll be used to perform the being logic. We'll look at that in a second. And you'll add that being task to the list. And then next, you'll create a thread pool executor. And this will require a little bit of additional knowledge. And we're going to cover this additional knowledge next week when we talk about some of the internals of the frameworks. And this will basically, when you create a thread pool executor, you'll have to tell it that you want a fixed size thread pool. So you have to say how many threads you want. And of course, the number of being threads will correspond to the number of beings. You'll have to give it a count. You'll also create a linked blocking queue that can be used to queue up messages if requests arrive for things to run and there's not enough things ready to run, and then not enough threads. And then you'll also give it an instance of a thread factory. And the thread pool executor will use this thread factory to make the appropriate kind of thread. And you have to figure out how to do that. So finally, after you've created the thread pool executor, you'll iterate through all the being tasks and execute each one of them on the thread pool executor. And because you've created a thread pool executor with the right number of being threads that were requested, they'll all get a chance to run concurrently. So now some of them won't run because they won't have a palantir to gaze at, but they'll all have the ability to run. So that's what you're going to have to fill in there. Let's take a quick look at being async task. So here's being async task. This is an async task, and you can see it's given a couple of parameters, a Palantiri presenter and a runnable, and then it returns nothing for the final parameter. This is what's passed to execute. This is what's passed to as the result of the publish progress and on progress result method, and then this is what would be passed to the as the return value of do in background. There is nothing we need to pass there. Much like before, we have an index that keeps track of the being in the list. We also have a countdown latch that's used to ensure everybody exits as a group. Those things get initialized properly here. I think it can probably be private final, if I'm not mistaken. And then over here, this is the do in background method thread. This is the one that runs in the background. So what it does is it pauses a little bit just to give a chance for people to get ready. And then it goes ahead and stores some variables that it's going to need. And then it goes into a loop. And this loop is going to keep running for I equals 0, I less than gazing iterations, which I believe defaults to 5. So it'll gaze by 5 to start with. Every time through the loop, it's going to check to see whether the being async task has been canceled. You have to fill in this code. You have to figure out how to do that check. So as the comment says, replace false with the appropriate method call to check if you've been canceled. And if so, you break out of the loop and shut things down. Otherwise, you're going to go ahead and basically make calls to show that you're waiting on the screen. And so you have to go and take a look at the methods that are used to show that you're waiting or gazing or idle and so on. And if you take a close look at those methods, they all return runnables. And so you're going to have to call those methods. You're going to have to take the runnables that come back, and you're going to have to pass them to the appropriate method in async task to communicate that runnable to the UI thread. So you'll have to figure out how to do that. It's very simple, but I want you to figure it out. Then you block waiting to get a Palantir, do a little sanity check to make sure things are going to work correctly. And then you go ahead and mark this thing as being used on the screen, show that you're gazing on the screen and so on. And these are, again, calls you'll have to make, calling the methods in the activity layer and then calling and passing the runnables that come back to the appropriate method in async task. So you're basically just filling in all these two do statements. And then when this thing is done, it's going to go ahead and release the Palantir, and we'll go ahead and return. Okay. So you also have to make sure that you correctly fill in on progress update, and that's an easy method call as well, but you'll have to figure it out to know how that works. There's a couple of things that are used to indicate at the very end that the thread, that the task is finished. And so in this case, the code is given to you. It just decrements the exit barrier by 1, and that goes ahead and will release the join thread when everybody is finished. Okay, so that's basically what you have to do for the async task part. Let's go take a quick look at the model part. So as before, there's just one file you have to look at here. This is the Palantiri manager class. And this time, it's very similar to what you did before, but rather than using synchronized blocks, instead, we're going to use concurrent hash maps, or a concurrent hash map. So I wrote it here for you. I gave you the definition of it. You have to fill in the constructor, you have to fill in acquire, and you have to fill in release. And an acquire and release are similar to what you had in assignment 1, except this time you use a concurrent hash map. And we'll talk more about concurrent hash maps next time as well. But the key thing to remember about concurrent hash map is that the methods you're going to want to learn how to use are put and replace. And really the magic of this whole thing is the atomic replace method, which is very cool. So you'll get a chance to learn how to use concurrent hash map, which is arguably even faster to use in many situations than using a hash map with a synchronized statement, although your mileage may vary depending on exactly the use cases that you apply it to. Okay, so that's basically it. So those are the things you have to do. The nice thing about this example is that it will build on what you did in assignment number 1 and then teach you some important ways in which async tasks compare and contrast to the approach that we used earlier that used Java threads. Okay, so why don't we go ahead and take a few questions if you have any questions. So let's see. Can we go over a minimal application that reproduces the MVP pattern to grasp a better understanding of how to deal with such a pattern? We'll be looking at other examples as we go through the course. The example here is sort of the canonical use of MVP. There are lots and lots of other examples that you can take a look at in the examples directory that also use MVP, and you'll see that they're all more or less the same. And the basic thing that you do, I'll just quickly sketch it to you just to explain how this works. Let's see if I can use this example to illustrate the point very quickly. So the way I do it, and my way is by no means the only way to do it. There are a number of other frameworks or libraries that you could avail yourself of to do MVP. If you take a look, if you Google MVP pattern Android, you'll see a whole bunch of examples that illustrate how to do the MVP. And so I strongly recommend that you take a look at that, and you'll find a bunch of different examples that illustrate how to do this. I don't have a particular preference of one versus the other, but you'll be able to find out what they do. So the way it works is, for Model View Presenter, we have several helper classes. We have this thing called generic activity, and generic activity is basically used to create a presenter object that is then connected to the view and also the presenter. So it's a way of connecting the view and the presenter together so that the presenter can call back to the view layer to do interactions with the user, and the view layer can call into the presenter to get various business logic processing done. So that's what generic activity does. Generic presenter does sort of the same thing, except what it does is it works together with the presenter layer and the model layer. So it creates a model, and then it finds a way for the model to potentially call back to the presenter, and for the presenter to call into the model in order to be able to get various sort of data related operations done, or interactions with data that reside across a network and so on. So those are two of the key portions here. And then there's also some other helper classes like context view, which we use to get access to view related operations, and model ops, which are some operations you get for a model, and so on and so forth. So those are some of the key interfaces. There's also something called presenter ops, which is something we'll see in a second. The way that this works under the hood for the presenter, the generic activity, is to use something called the retain fragment manager. And I will also do a video later in the class that goes into more detail about the retain fragment manager. And the retain fragment manager is basically used to detect automatically when the screen rotation occurs, and then to make the appropriate callback hooks into the presenter layer to update its notion of what the view is. So we'll look at all those things in more detail. And there's this file called the MVP file, and the MVP file essentially defines the interfaces that each layer either requires or provides. So when you have a required interface, that's an interface that's offered to another layer. For example, the required view ops are the operations that are offered from the view layer into the presenter layer. And so these are the things that are basically callbacks that are used to talk to the view layer from the presenter layer. We then have provided presenter ops. These are the operations that are provided from the presenter layer up to the view layer. So things like start and so on, configuration change occurred. These are methods that the view layer calls to get information from the presenter layer. Then we have the required presenter ops, which are the things that are needed by the model layer. And let me zap this one because we don't actually need this in this particular case. It really is just a sort of a no op. We don't need to have that there. And then we have provided model ops, which are the methods that are provided by the model layer up to the presenter layer. So these are the things for making Palantir and acquiring a Palantir and releasing a Palantir and so on. And so these are all the methods that the model layer offers up to the presenter layer. So what we're doing here is we're being very, very decoupled between the layers. The layers don't know anything about each other except what they are being exposed through these interfaces in the MVP file. And then all we do is we simply break our program up into a view package, a presenter package, and a model package. And then each of these packages will then implement the appropriate part of the framework. So for example, gazing simulation activity is a generic activity, and it's going to basically provide the required view to the activity, and it's going to implement it's going to know something that it'll have an accessor method that will return the methods that are implemented by the presenter object, and then it'll give a class that's actually used to make an instance of the presenter object. And so, and then of course it implements the required view ops. These are the ones that it exposes to the model layer, to the presenter layer. And then down here, when we call this method, which is what comes from the generic activity class, is actually going to pass in the Palantir presenter class, which will be used as a factory to make the appropriate presenter layer object. And it will pass this object as the interface that's going to be available for use by the presenter layer. So that's how we connect the two things together. So that's the way that the presenter layer gets created and the view layer gets connected to the presenter layer. And then the same thing happens over here with presenter. We simply are going to have the same basic idea. We have a generic presenter, which will define several operations it exposes to the model. We'll have the model layer's operations that are exposed to the presenter, and then we'll have the class that will implement the model implementation and the model layer. And then down here, you can see that we go ahead and create the model, the presenter object, but we do it in such a way that we make ourselves, the model layer. And the model layer object will be created from this class, and the presenter will be passed in as the interface that's exposed to the model. So everything basically works like that. And if you take a look at the other examples, you'll see many examples that have the same thing. Okay, so that looks like those are the questions that we've got. If you have any more questions, I'll be happy to take them. Otherwise, thanks very much for joining, and please continue to be active on the discussion forums. Thanks.